Okay, you guys, time to do some math.
Okay, in this video we are going to look at trigonometric limits. And I want to begin with this example. This is a sort of famous example. It's a tricky limit problem that shows up in various forms from time to time. So we're going to understand this limit and then use it to answer some more difficult limit problems. If we begin this the way that we begin everything, by seeing what happens with our direct substitution method, we end up getting the sine of 0 divided by 0, and the sine of 0 is equal to 0, so we end up with indeterminate form, so it's back to the drawing board. So we could look at this numerically. I'm choosing to show you this graphically right now. As we approach from both sides an x value of 1, this function is coming up here to 1, and technically this graph isn't showing it, but there is an open dot at the point 0, 1, because as we've just shown, when you plug 0 in, you get indeterminate form out. There's no output value when x is 0. So this limit does in fact equal 1. And hopefully I have convinced you of that graphically. So let's look at some extensions of this. And I would tell you that this is a function that is probably worth just knowing and memorizing so that you're not left to graph this thing every time. This one will show up frequently enough that it would be worth knowing. So let's look at this example. The limit of sine of 5x over x as x approaches 0. Again, if we try to plug 0 in, we get indeterminate form 0 divided by 0, so we can't do that. We've got to think through what we can do. Algebraically, there's really not much that we can do. If it was sine squared, it might be a different story, but it's not sine squared, so we need to lean on our knowledge of the previous limit. So you'll notice that this looks kind of like our example that we're trying to solve, but what we really want in order for us to know that this thing is equal to 1 is that whatever is inside the parentheses needs to be the same as the denominator, and if that's the case, that limit will approach 1. So let's see if we can make that happen, if we can manufacture that. What would be great is if there was a 5 connected to that x. So let's put one there. If we put one there, we've got to put one up north as well. So what we're doing is we're multiplying our fraction by 1 in the form of 5 divided by 5. So now this portion is looking just like this. If we go ahead and pull this 5 out front, using our constant rule as our property of limits, we will be in pretty good shape. So the value of our limit is equal to 5. Alrighty, so here's our next example, the limit of sine of 7x over 3x as x approaches 0. This looks pretty close, but it's still not quite what we want. So let's do the same thing that we did last time. It would be great if this denominator here could be 7x. So I don't really want to multiply 3 by something to get 7, so I'm just going to go ahead and multiply it by 7, multiply the numerator also by 7. And if I simply shuffle things around, if I move the 3 and the 7 on the denominator, I can kind of see the grouping here. What I'm going for is the sine of some quantity divided by that same quantity, because I know that the limit of that quantity, which before we were just calling x, but as long as they're the same, it's good. I know that that limit is equal to 1. And again, here I have a constant of 7/3 that we can pull out front and go from there. So we end up with 7/3 multiplied by this quantity, which is equal to 1. Alright, so try plugging in 0, you get the tangent of 0 divided by 0, and remember that the tangent of 0 is the same as finding the sine of 0 divided by the cosine of 0. The sine of 0 would be 0, and the cosine of 0 would be 1, and 0 divided by 1 is 0, so we end up with 0 divided by 0 again when we use direct substitution, so we're left to algebraically change something. And this is an example where we actually can do something using this same knowledge that we used here, that tangent is equal to the sine divided by the cosine. So here we go. Be careful, this is our big division sign. Right there, sine of 5x divided by the cosine of 5x all over x. Let's see what we can do with this. We can multiply this guy by the cosine of 5x over 1. Those cosines will cancel. And then we've got to do the same thing on the denominator, cosine of x over 1. Oh, and look at that. Back here I forgot to put a 5. Hopefully you caught that. So here we are with the limit as x approaching 0 of sine of 5x over x times cosine of 5x. Just for kicks, let's try again to plug 0 in at this point and see where we are at. Plug 0 in and you get the sine of 0. We've already talked about how that equals 0 divided by 0 times whatever it is going to be 0. 0 divided by 0, we're still in indeterminate form, so we've got to do something else. Now, here we go. We have the sine of 5x. We would like this to also be 5x, because then this we can deal with in the way that we know how to deal with the other examples that we've looked at. The sine of something divided by itself, as the limit goes to 0, will be 1. So we're going to go ahead and manufacture that again. We're going to make this 5 and put the 5 up top as well. Alright, so the jump from here to here, let's just make sure that you're on board with what I've done. I've taken this constant 5 and I've pulled it out front. And now I've broken up this fraction into two fractions. I've separated the sine of 5x over 5x into one quotient, and then I've written another fraction with the cosine of 5x on the denominator with one up front, or sorry, one up top. And by doing this, I can clearly see that this is going to offer me the same thing that the other examples have offered me, which ultimately will be that it equals 1. The trouble is, the way that it's set up right now, if I just plug 0 in, I'm going to end up with 5 times sine of 0 divided by 0, which is indeterminate, divided by 1 divided, or multiplied by 1 divided by 0. On this quotient right there. So if we were to write that all out, it would be 5 times 0 divided by 0 times 1 divided by 1, which we can't multiply by an indeterminate form. So we are going to split this thing up using properties of limits, and then we'll clearly be able to see that this middle piece actually is equal to 1. And you can probably see that now, but just for the sake of writing this in a technically correct way, let's use our properties that allow us to take the product of two quantities and write this as the limit of the first multiplied by the limit of the second. So here we have it. We have our 5 out front. That's going to still be 5. This limit is equal to 1. And now when you plug 0 in to this denominator, you still get the cosine of 0, which is equal to 1. 1 divided by 1 is 1. So we end up with 5 times 1 times 1, which is equal to a value of 5.